So what you've just seen there is some footage I captured recently of an electrical storm. And it really got me thinking, why don't I give a little bit of an explanation about how those processes go about generating such majesty, such amazing propagating electricity of fractal patterns and dendritic spines. It still leaves me in awe, no matter how many times I see it. And hopefully I can clear up some misconceptions that people might have about electrical storms or lightning in general, because contrary to what many people might think, it is in fact not Zeus beckoning from the heavens to instill a sense of dread and mortality into us. So with that being said, let's get right into it. So electrical storms generally result within a special classification of cloud known as cumulonimbus. And cumulonimbus clouds have a charge separation where one boundary has predominantly positive, so we'll say that's the top layer, where it's almost concentrated entirely with positive charge, and the bottom layer is concentrated predominantly with negative charge. And this happens to be a precursor mechanism known as polarization. And polarization results due to a phenomenon known as frictional charging. And frictional charging is probably familiar to many of you who've ever decided to rub their feet along the carpet and decide to either poke or prod your friend or sibling and giving them a little pleasant jolt. Well, it is very analogous to that, because you are picking up electrons, and these electrons are coursing through your body just waiting to be discharged until you decide to go and ground yourself on the next unsuspecting victim. Now, this draws a lot of similarities with electrical storms, but the one main difference is these frictional charges are generated through particle collisions. So when the moisture in the cloud is elevating, rising to the top of the cloud, millions of little particles constantly in turbulent motion are running into one another. And as they're running into one another, they're undergoing that frictional charging we just talked about. And once they rise to the top, there is a concentration predominantly consisting of positive charge. So that would only necessarily leave bottom negative. Now, these negative charges have their own electrical field, and this electrical field stretches all the way down to the surface of the Earth and effectively grabs the positive charges and pulls them to the surface by a process known as induction. Now, when those positively charged particles are pulled to the surface of the Earth, the negative ones are being repelled away further into the Earth. And this consequence is something you may have experienced before if you've ever played with a magnet, where you took the like ends of the magnet and tried to bring them close together, and you felt that pressure, that outward pressure, trying to prevent them from making contact, whereas the opposite ends naturally attract one another. This is, in essence, the same principle working here. Now, over time, an electric potential gradient permeates through the air between the cloud and the Earth itself. And as time builds up, this electric potential is becoming larger and larger, and once it reaches a certain threshold, it will naturally discharge all of its electrons and surging all the way towards the surface of the Earth. And this surge isn't just one single surge, it is a sequence of oscillating currents going back and forth millions and millions of times per second, because we are incapable of visually seeing that going on. And this bolt alone generates a voltage on the magnitude of 100 million, which is astonishing. This, in fact, corresponds to 30,000 amps. And I hope that gives you a little bit of a sense of appreciation for just how amazing these phenomena are. Now, what I would like to illustrate is how this actually happens as opposed to explaining it. So with my terrible artwork, hopefully you can get a little bit more intuition as to what's going on here. So at the surface of the cloud, the top layer, we're going to have positive. So positive charges residing right here due to the charge separation or polarization, as we mentioned before. Now the negative charge will naturally be left right here at the bottom. Now, and through a process by induction, as I've already explained, we have positively charged particles being pulled to the surface of the Earth. So you will see positive primarily right here. And even in other materials, such as this house here, there will also be electrons flowing through it that will be induced. So positively charged right here. And then along the surface here, positive as well. And as I mentioned before, the negative charges are just going to be repelled away, not really interacting at this moment. You get the point. Now, over time, that electric potential gradient is building up more and more until that threshold moment where you see this surge of electrons propagate all the way to the surface of the Earth. And I hope my artwork at least gives you a little bit of a sense of what's going on here, along with the explanation, of course. That being said, the air itself works and functions as a really effective dielectric. And if you're not familiar with that, a dielectric essentially is a medium at which negates the flow of charge passing through it. And better dielectrics negate more charge flowing through it, and air functions as a very effective one. And the only reason that lightning is able to propagate through this medium is because of this electric field that builds up over time, more and more, to the point where the air around it effectively ionizes and turns into a conductive plasma. And if you're not familiar with what a plasma essentially is just when a gaseous molecule has its electrons departed from it, and it allows it to be more conductive. And that might be an oversimplification, but hopefully you at least understand the idea there. And that being said, when lightning strikes, it generates an immense amount of heat, up to 30,000 degrees Celsius. And this happens to be around 5 times hotter than the surface of the sun. And that heat that surrounds the bolt that you see, in fact, creates an outward flow of pressure that generates that loud boom sound that we now know as thunder. So when you see a lightning bolt and then subsequently hear the thunder afterwards, you now know that it is simply just an outward flow of pressure moving so rapidly that it essentially breaks the sound barrier and creates that sonic boom that we now hear. Now that you have a pretty good conceptual intuition as to how lightning behaves, I would like to give a little bit of a demonstration into the tools that we can use to describe this system as a whole mathematically. Now, it is very difficult to make predictions about when lightning will strike, which is why we haven't yet been able to harness this electricity and provide our entire world with free energy. Obviously, people have thought of that before, but we at least have some tools into describing a displacement current along with the associated time-varying electric field. So with that being said, let's get started. So the first equation we're going to need here is the continuity equation. And the continuity equation is d rho with respect to time. And rho just represents the charge density. And then we're going to add that to del. And del is a gradient operator which describes a vector field in a vector space. Probably worth another video, but for the purposes of this one, this is all we need. And then we're going to multiply that by J, which is the current, and set it equal to 0. Now, we're going to use another equation, and this equation is one of Maxwell's equations. And that one is describing an electric field, where we have del times E, being the electric field, equal to rho, which is the charge density, as we established, divided by epsilon naught. And epsilon naught here is known as the permittivity of free space, which describes how much a vacuum can permit an electric field, essentially. It is a constant that is very useful in electrodynamics here. So that being said, what we want to do here is bring this epsilon naught factor over to the other side and set it in terms of rho, or the charge density. So rho is equal to gradient operator times epsilon naught times the electric field. And now what we want to do is differentiate both sides. So we're going to have d rho with respect to time is equal to the gradient operator here times epsilon naught, and then d e dt. Okay, at this point now, we can take this equation and plug it in for this other factor of d rho dt. So that will give us our gradient operator times epsilon naught times the change in electric field here, dt, and that is going to be added to del times the current is equal to 0. Now what we can do is factor out this operation factor, this del operator, and give us our net result, which is del times epsilon naught dE dt times j, and that is equal to 0. Now, what we have here is the final equation that is very helpful in describing a time-dependent system or displacement current with a time-varying electric field. And this factor right here is generally attributed the symbol Jm, or the letters I should say. And the simplified version will give us something like this. So del times J is equal to 0, Jm. And Jm has many different contributions, which is why it makes it so difficult for predicting these electrical storms and where lightning will be touching down. And it's generally this system as a whole is considered a quasi-steady system. And if you're unfamiliar with the quasi-steady system, it is a state approximation of a system in which one component of the system is moving slower than the other part of the system. And the faster moving portion is moving so fast it reaches a state of equilibrium to where you can consider the totality of that system constant. And it makes the calculations a lot easier. That being said, this contribution right here is essentially the sum of many different kinds of currents. So that consists of convection currents, which gives us charge transformations and precipitation currents. You have local field dependent currents. And additionally, there's another set of components consisting of the ohmic and corona contributions. So as you can see, there's a lot to this factor here, which makes these calculations so difficult. But nevertheless, it is quite impressive that we're able to even describe these phenomena at all, which is why I enjoy it so much. So that being said, I hope you at least learned something here today and gained a sense of appreciation for our natural world and what we can use to describe them. Now, if you have any further questions, don't hesitate to reach out to me and ask, and I will be glad to elaborate on anything at all. That being said, have a wonderful day.